Yo, yo, yo. All right, so today I want to go over complex numbers. And this is kind of like a topic that you learn in algebra. And it comes back at you, way back at you in bigger math, like differential equations, linear algebra comes up a lot in electrical engineering, aerospace engineering, mechanical engineering, pretty much almost anything that has anything to do with like spring or harmonic motion, oscillating stuff, oscillating parts, stuff like that, almost always comes back. There's actually a whole field of mathematics dedicated to this called complex analysis, which was one of the it was one of the better classes that I've taken so far. Super interesting, super cool in my opinion. But anyways, so let's get into it. So basically, what is a complex number? The type of numbers that you have that you know at this point or have gone over are whole numbers, natural numbers, right? Whole numbers like, one, two, three, four, five, six, you go on, right? Natural number is basically just a whole number that starts at zero. So now you have, because they're natural, right? We have either nothing of something or we have positive of something, right? Zero, one, two, three, four, five, right? We have fractions like quotients, right? Which is just essentially some like integer over another integer, right? And we have integers, right? 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5, right? All that stuff. We have real numbers, and real numbers are the ones that I think everyone intuitively knows. We have 1 through 10, but we also have 5.5. We have 5.6666666. We have 1 point something. All the itty bitty ones in between, right? As well as their negatives, complete opposite too. So really, what a so in order to understand complex numbers, we need to understand what a real number is and what some of those other stuff are. So let's start off with the general form of a complex number is this guy right here, which is a plus or minus bi. So where a and b are elements of the real number system, right? They can be pretty much any number you want. They could be zero, they'd be negative 250.7, they could be 3,500,000, right? They can go either way, whatever. That's pretty much it. Now, you will notice that you see this thing I here, right? And so, well, what exactly is I? It's this weird letter. Well, I is defined as being equal to the square root of -1. Now, if you remember anything from algebra, you're not allowed to take the square root of a negative number, right? This necessarily can happen. Turns out you actually can. And it is defined as an imaginary number because we don't think of this as actually existing. It's imaginary to some degree and has a lot of interesting properties to it. I think if I remember right, Euler was one of the first ones, was one of the first people who did this stuff. Cauchy did some stuff later on with it, but anyways, that's history lesson for another day, right? So anyways, in algebra, let's just go over with what they want you to do with it from an algebra point of sense. So let's just say, let me put this to the side here. Let's just say you have two numbers, right? You have two complex numbers, right? And let's just do 2 plus 3i. Let's just say plus 1 minus 2i, right? And we want to figure out what this is equal to, right? So what is this equal to? Well, what we're essentially going to do is we're going to combine like terms together. We're going to put all the a's together, then we're going to put all the b's together, right? Essentially, when it comes to addition and subtraction, nothing different, nothing new that you haven't done here before, right? So what does this mean? Well, we're going to take all our a's together. In this case, the 2 is your a and your 1 is your a, and you're going to add those two together. So 2 plus 1, that's simply equal to 3, right? Now you need to take the other terms, which are your imaginary terms. You're going to take the 3i, and you're also going to take the negative 2i. You're going to be adding those together. So 3i plus a negative 2i. So 3i minus 2i is going to give you a positive I, right? And again, this number should be in the general form of a plus bi, which it is. A being equal to 3, and then I being equal, or sorry, B being equal to 1, right? And that covers the topics of addition and subtraction. So when it comes to multiplication and division, kind of forget division right now because it's really just the reciprocal of multiplication. If you figure out multiplication, you'll understand division. I won't even go over division. So let's assume we have the exact same problem. All right, and I will erase this guy. Except now these guys are multiplied by each other, right? Cool. So you're multiplying two parentheses together worth of stuff. You learn the FOIL method, same easy thing, right? So 2 multiplied by 1, what is this can equal? This can equal 2. 2 multiplied by negative 2i, multiply the numbers together, keep the I, and make sure you check your signs. So 2 multiplied by negative 2i is equal to negative 4i, right? Let's do another color for this one. 3i times 1, and then 3i times a minus 2. 3i times 1 just going to be positive 3i. Positive 3i, right? And now we get to an interesting one. Now we get 3i multiplied by a negative 2i. Okay, so first things first, let's figure out the sign. So positive 3i, negative 2i. Negative wins, right? Positive, negative, when you're multiplying, negative always wins. So negative. All right, take your b's. In this case, it's a 3 and a 2. Multiply your b's together, put it there. 3 times 2, 6. All right, now you're left with I still. Now you're left with I multiplied by I. Well, we previously defined I as being equal to the square root of negative 1. Essentially, what we're asking for here is I multiplied by I is equal to the square root of negative 1 times the square root of negative 1. Or you can also define this as negative 1 to the 1/2 power times negative 1 to the 1/2 power. Remember, when you're multiplying numbers together that are to a certain exponent that have the same base, you add the exponent, right? So in this case, your base is going to be negative 1 still, but your exponent is going to be different. You're going to do 1/2 plus 1/2 because it's the same base. So 1/2 plus 1/2 equals 1. You have negative 1 to the first power, which is just equal to negative 1. Therefore, I times I is equal to negative 1. Cool. Now that we know that, let's multiply a negative 1 by this negative 6. Two negatives equal positive. So we're just going to change that sign. Still not done because this number here is not of the form a plus or minus bi. We have 4 terms here, not 2. Let's combine like terms, get it together. So what are the 2 terms that are like each other? 2 and 6, right? Let's add those together. 2 plus 6 is equal to 8. Then we have negative 4i plus 3i. Add them and subtract them the way you'd normally do for anything else. In this case, it's equal to negative I. 8 minus I. And so this is your final answer, right? Pretty much it. It's very straightforward. It's really what they want you to do when you're doing algebra. You're going to get to a little bit, you're going to get to some different stuff when you get into complex analysis and whatnot. And just very briefly, I'd kind of like to go over that. One of them being that, let me see if I can right here. So let's make a graph. Cool. Excellent. All right. So way back in the day when you're doing algebra, or maybe you're still in algebra, you were asked to draw a graph, maybe just say the equation of a line or anything like that. And it was on an XY plane, right? So your horizontal axis would be your X's, your vertical axis is your Y's, right? In this case, when it comes to complex numbers, this is going to change. So your horizontal axis is actually going to be your what's called your real domain for all your real numbers. Think of your A's, right? And then your vertical axis is going to be all your imaginary numbers. So think of your I's. I'll just put I here, right? So if we wanted to graph, let's just say graph, let's just do 1, let's write this better. Let's just say graph 1 plus 4i. Okay, what this is essentially telling us is that we want to graph one unit in the real domain, the real direction, right? So we're going to go over one unit. Let's just say this is 1 unit, right? We'll make this go 1, 2, 3, 4, 5. Let's just go 1, 2, 3, 4, 5, right? Just to make it even. And we want to go up 4 units in the imaginary direction, right? So let's go 1, 2, 3, 4. We're going to be over here, right? Because we're going to go up this much. And what we're going to do is we're going to take a arrow all the way from the origin all the way up to that point. And essentially, that is what our graph should look like. This is your, they call it a vector. This is your vector 1 plus 4i, right? So 1 plus 4i. So that's pretty much what you do to graph in the complex domain, right? Remember, if you go just in the real domain, you're going to have your x's and y's. If you go to the complex domain, your real axis turns on the vertical, your imaginary axis goes up. You just plot it like it is. It's not that bad, right? Pretty much it. There's more I could talk about when it comes to, let's just say, when it comes to this stuff. Let me see if I can erase it. One of the largest things that ended up going on when it came to complex analysis, and this is just sort of a, well, let's just maybe go over this. It's Euler's identity. This is a very useful tool in anything math, engineering, physics, useful in complex analysis. It's like the fundamental basic for it. And really what Euler's identity says is you're going to have e to the I multiplied by theta is equal to sine of theta plus I cosine of theta, right? And let me check something out here real quick. Actually, you know what? I messed up a little bit. It's been a while since I've done this. I thought so. So actually, I got this guy around. This is about to make the same mistake. This is actually cosine of theta, I times sine of theta. Okay. So essentially what this is saying is that if you take any in any theta can be any number, any angle, whatever it is, right? E, which is just a mathematical constant, 2.718. If you raise that number to the I times your theta power, this is what you're going to get. You're going to get a bunch of sines and cosines, right? But essentially, what does this kind of look like to you? This should kind of look familiar, even though it's a little bit scary because your algebra intuition should still be the same. You have cosine of a real number plus I multiplied by sine of a real number. Well, cosine of a real number is just a real number. And then sine of a number is just a real number. So really what this boils down to, let's write this in pink, e to the I theta, where theta is defined, is essentially equal to a plus I times b, a complex number. Nothing changes from algebra. It just looks scarier. Pretty much it, right? And you can go on and be like, well, what if there's a negative here that's going to put a negative there, right? You can go on with that. And there's actually proofs for this. If you're really interested in it, you could take the power series of both cosine of theta times along with sine of theta, push them together, take the power series of e to the I theta, you'll notice that they both basically add up. Anyways, but for the most part, that's pretty much complex numbers in a brief introduction to sort of higher up complex analysis, what they kind of do, right? Anyways, hope you enjoyed it, and thanks.